Hey guys, in this video I will present a solution to Bulgaria National Math Olympiad 2014 problem 4. Firstly, we'll have a look at the statement. We are asked to find all pairs of primes p, q for which the following two divisibility conditions hold. P squared shall divide q cubed plus 1 and q squared divides p to the power of 6 minus 1. When dealing with divisibility conditions, we would like to make factorizations. And in this case, this looks pretty easy because we know how to factor the right-hand sides of both of these terms. So, firstly, let's take a look at what this gives us. Well, we have p squared divides q cubed plus 1, which is nothing but q plus 1 times q squared minus q plus 1. Taking a look at this statement, we can immediately use the fact that p is a prime, because this gives us only finitely many cases for how p can divide both factors. The first being that p squared alone could divide q squared minus q plus 1. If p squared does not divide q squared minus q plus 1, then because p is a prime, we get that p divides q plus 1. The reason for why I divided all the possibilities into exactly those two cases is that they give us nice bounds on the size of p with respect to q. So firstly, from this we can immediately see that p squared is less than or equal to q squared minus q plus 1 because this is not 0. So p is less than or equal to the square root of that, which is obviously for q greater than or equal to 2, less than q. The other case does not immediately give us such a nice bound, because here we only get that p is less than or equal to q plus 1. But we see that here we have more potential, because, well, we know that for most primes, in fact exactly if and only if q is odd, then the right side is going to be even. And for most primes p, if and only if p is odd, p is co-prime to 2. So in most cases we can deduce from that that p also divides q plus 1 all over 2, which will give us the same bound. This motivates us to take a look at the possible values for q when p is 2 and the possible values for p when q is 2, and from then on to assume that both are odd primes. So let's do this. From p equal to 2 we get that q squared must divide 2 to the power of 6 minus 1, which equals 63, or 3 squared times 7. So the only prime solution for that is q equal to 3. And we can also plug those values into the first equation, and clearly 4 divides 3 cubed plus 1, which equals to 28. So indeed 2, 3 is a solution. Furthermore, plugging in q equal to 2 tells us that p squared must divide 2 cubed plus 1, which equals to 9, or 3 squared. So since p is prime, we get that p can only be 3. And since 3 is congruent to 3 mod 4, we also get that 3 to the power of 6 minus 1 is divisible by 4, and therefore 3, 2 is also a valid solution. Now we have determined all the solutions for p and q equal to 2, so from now on we can assume p, q greater than or equal to 3. As I've already said, knowing that, we get a lot of information about this statement as well, because for that case p divides q plus 1, which is even, although p is odd, so we also get that p must divide q plus 1 over 2, and since q plus 1 over 2 is positive, we get p is less than or equal to q plus 1 over 2, which is clearly less than q for q greater than or equal to 3. So by our factorization and using the fact that p is a prime, we get out of that that p is less than q in any case. Now we would like to take a look at the second condition. Immediately we also see that p to the power of 6 minus 1 is factorizable. So we get that q squared divides p to the power of 6 minus 1, which equals p cubed plus 1 times p cubed minus 1, and that is nothing but p plus 1, p squared minus p plus 1, p minus 1, p squared plus p plus 1. We can take a look at these factors on the right hand side. And we immediately see that p minus 1 is less than p, which is less than q. So any factor of p minus 1 is also less than q. And since q is a prime, we get that the GCD of q and p minus 1 equals to 1. This is really nice because now we also know that q squared must divide the product of these terms. The next candidate for doing similar stuff is p plus 1. Because we know that p and q are both odd primes and p is less than q. So p is at most q minus 2 and therefore p plus 1 is less than q. Which tells us that the GCD of q and p plus 1 is also 1. Combining this information with this divisibility condition, we conclude that q squared divides the product p squared minus p plus 1 times p squared plus p plus 1. We recall that p is less than q. So we would like to use this fact to get a contradiction out of this. For instance, we can immediately see that q squared cannot divide p squared minus p plus 1 because it is simply too large. It also seems unlikely that q squared can divide p squared plus p plus 1 because q squared can't be much smaller than this. But this argument fails for when q only divides p squared minus p plus 1 and the other factor exactly once. This motivates us to take a look at the greatest common divisor of those two factors, which in this case q should divide. And we can compute that GCD and get that the GCD of p squared minus p plus 1 and p squared plus p plus 1. To compute this, we can use Euclid's algorithm that works for polynomials just like for integers. So we get that this is equal to the GCD of p squared minus p plus 1 and the difference of these two terms, which is nothing but 2p. Clearly, 2p has exactly two prime divisors, namely 2 and p. Now, p squared minus p plus 1 is congruent to 1 mod 2, so this GCD is not divisible by 2. Furthermore, this is congruent to 1 mod p, so p also does not divide this. Therefore, all of this equals to 1. Now, we remember why we considered this greatest common denominator. Because in the case that q divides both of these factors, it must also divide this. But since the GCD is equal to 1, we know that g does not divide the GCD of those factors, and therefore either q squared divides p squared minus p plus 1, or q squared divides p squared plus p plus 1. And I already said that because it is too large, q squared cannot divide p squared minus p plus 1, so we conclude that q squared divides p squared plus p plus 1. And now we will finish the proof with our improved pens. We see that q squared is at least p plus 1 squared because q is greater than p. Now this is equal to p squared plus 2p plus 1, which is clearly larger than p squared plus p plus 1. But q squared should divide this quantity, and this is of course a contradiction because p squared plus p plus 1 is greater than 0. And therefore we are done in this case and get no solution other than 2,3 and 3,2.